Okay, I think I see 3:03 on the clock, so I propose we get started without too much further ado. It's my pleasure to welcome you all today on Pentecost Monday, so thanks for joining us to this month's installment in the Athena X-ray Advances webinar series. Today our speaker is Efrain Gatuzz, so welcome. Just a little bit about the speaker. He graduated with his PhD from the Venezuela Institute for Scientific Research in Caracas, and then he moved to Europe. And since so he graduated in 2015, and since then he's been sampling the many fine institutes of Garching, Germany, first as a postdoctoral fellow at MPA, then as an excellence cluster fellow at ICO, and currently a postdoctoral fellow at MPE, all of them in the same area. But he seems to be enjoying Germany. It's nice to have you in Europe with us. And the title of the presentation today, or the topic of the presentation, will be about velocities in the intracluster medium due to sloshing, merging, and feedback. And with that, Efrain, the floor is all yours. Please go ahead.
Thank you. Thank you for the presentation. Yes, let's talk about velocities. First, I want to mention, of course, my collaborators on this project that we have been carrying on in the last couple of years. The first question that I want to answer is why measuring velocities in the intercluster medium is important. So there are many reasons for that. Here I have a summary of them. First, we know that turbulent motions, particularly at large radii, affect calculation of hydrostatic equilibrium and cluster mass estimates. So it is important to take that into account. Otherwise, we will have inaccurate mass estimation for the galaxy clusters. And we also know that from simulations that there is a close connection between multiple observables within galaxy clusters, including entropy, temperature, density, pressure, and velocity power spectra. So, for example, here we have a plot of the. I hope you can see my mouse, by the way. Perfect. We can see here a plot of the luminosity and the effects of the velocity for different line of sight for the luminosities that we can recover. We also know that the motions will cause the transport of metals within the ICM due to sloshing and uplift of metals by AGNs. So we know that the elements distribute between the galaxy cluster, depending also in the cinematics of the cluster itself. From simulations, we also know that there are some structures related with the gas sloshing, like, for example, these spiral patterns that we can identify in many simulations. And these structures remain for several gigayears. So we should be able to identify such structures, and then they are associated with the gas sloshing itself. And this can be identified if we map the velocity structure between the cluster. So it is important. I will mention by first time, and I will mention that later on, that all the science cases for future observatories, for future X-ray observatories, especially those that include high resolution spectra, include the velocity structure of the galaxy cluster as part of the science case. So it is important for the current generation, and especially for the future generation of observatories, including Athena, of course. Well, what can we do right now to measure velocities? I would say is very limited, but there are some measurements that we can do. Using high resolution spectra, and talking about the HETG and RGS cameras on board of Chandra and XMM, we can measure velocities of galaxy clusters in the cluster core. So that's one limitation. We are only measuring velocities very, very close to the cluster center. And for many of the clusters, we only have upper limits, as you can see, for example, top right panel. Typically, velocities obtained using these methods are of a few hundred kilometers per second. Another way to do these kind of measurements, an indirect way, is through measuring surface brightness fluctuations. In both cases, we have found, or people have found, low velocities in the sense of few hundred kilometers per second. Direct measurements of the velocities are really difficult, and the way to do this is using, for example, microcalorimeters. So we have observations from Hitomi for the Perseus cluster. For the central part of the Perseus cluster, we have found low velocities, 100 kilometers per second, which is interesting because we are talking of a very complex system with a lot of things going on in the central part of the cluster, but still we found low velocities. So from the simulation side, there are simulations that include the AGNs. There are simulations that do not include the AGN, and still you can recover these low velocities for many systems. But we only have measurement for Perseus, which is really sad in the sense that, well, we lost Hitomi, so we will not be able to make future measurements. But there are new observatories on the way, at least one. We are sure that this year, I hope, Chrism Observatory will be launched. For future, there are proposals like LEM and of course Athena to do observations of the velocities, direct observation of velocities in the line of sight for galaxy clusters. So that's it. But in the last years, a new method to observe velocities to measure velocities in galaxy clusters was proposed. That's the core of this talk. How can we do velocity measurements using XMM-Newton EPIC PN cameras? So the basics of the methodology is here in this slide. We can see here the EPIC PN camera. This is CCD resolution. And you can see the CCDs, you can see the field of view. You have here an area called Cooper Hole. I will talk about that later. So the basic idea is from the detector, from the EPIC camera, you have instrumental lines, instrumental emission lines from the electronics. And the lines are here in this plot. You can see the Cooper line, K alpha line, nickel, zinc. These lines are close to the iron K alpha lines. So what we do is to use these lines to improve the energy calibration scale. And now we are able to measure velocities using EPIC camera with uncertainties down to 100 kilometers per second, which is fantastic for CCD camera, of course. There are some caveats. We need bright sources. We need really good statistics to do this. And another thing is that, as I mentioned before, there is something called Cooper Hole. And you can see here the image that the central part of the detector does not show these emission lines, these instrumental lines. That means that you cannot apply this technique to the central part of the detector. So you see, if we want to use archive data, okay, we cannot use this for all of the clusters that we have. For example, in this paper, in the paper Sanders 2020, when we show the methodology, so they apply this method to measure velocities within the Perseus cluster and the Coma cluster using the data in the archive. So that means that for the central part, there are no measurements of the velocity. But still, there are, here you can see for the Perseus cluster, for different regions, the velocities obtained. And one interesting result is that one region covered by Hitomi can be analyzed with the method, and the velocities agree with better uncertainties for Hitomi, of course. But still, this is a good support of this methodology. And then we have for the Coma cluster different velocities, and you can see that for some regions there are really high velocities. We are talking about 1,000 kilometers per second. But this is, or the explanation for that is that these regions with high velocities are close to one of the groups within the Coma cluster. So it's kind of expected that the gas is moving at those velocity on these regions. So that's the methodology, the basics of the methodology, which is a nice exercise, by the way, I think, to think about how to use something that usually you don't want to use, in this case, instrumental lines, to improve your measurements. Okay. For the analysis of the Perseus cluster in this paper, there are some hints of gas sloshing patterns. So you can see here the surface brightness residuals, the velocity map in the center, and the temperature map to the right. And top panels are simulations, and bottom panels are the measurements from XMM. And there are hints for the velocity maps. Blue means blue shifted gas, and red means red shifted gas. So there are hints here for a spiral pattern associated with gas sloshing. So this is a direct evidence of such sloshing between the ICM. But as I say, you cannot apply this method to the central part of the detector. So in the last 5 years, we have applied for several large programs to observe again some of a variety of clusters to analyze the velocity structure between them. Today we talk about the results obtained for 3 of these clusters: Virgo, Centaurus, and Ophiuchus. So why these sources? Well, they are very different between them. That will allow us to study different scenarios for the velocity structure. For example, for Virgo, we know that we have beautiful central jet, we have large radial bubbles. We know that there is heavy interaction between the IEN and the ICM in this cluster. For Centaurus, we also have the presence of jets, the AGN, but also there are dynamic subcomponents for this galaxy cluster. The AGN appears to have been active multiple times or long time scales. Ophiuchus is different. It's hot cluster. It's massive. It's relatively relaxed, and there is no powerful AGN in the center. So this is a different scenario. Here you can see the ideas of the proposals that have been approved for us. So let's move forward. And as I say, we need high statistics. We need large exposure times to apply for this. So these are our large programs. And also, as I mentioned, we cannot apply the method in the central part of the detector. That means that in these programs, we do multiple offset observations in order to cover the central part. So the left image is the X-ray image. And you can see the point light sources removed from the analysis. We also remove, in this case, the very center of the galaxy cluster due to the presence of the AGN. Top right, you can see the exposure maps. We use archive data, but also, of course, the new observation that covers the central part of the cluster. Because the field of view XMM, we can analyze region from the cluster center up to more or less the outskirts regions of the cluster, which is good. The bottom right panel shows the distribution of, well, this is a map of we can see the number of counts or the statistics around the Aron K alpha complex. So you can see how a good statistic is obtained for the central part of the galaxy cluster. And you can see also these holes, which correspond to the Cooper hole, the region of the detector where we cannot apply this method. So let's talk about the results. So this is velocity. The velocities that I'm showing are velocities in the line of sight. The velocity map for Virgo cluster is in the left side, and the color means that blue is blue shifted gas and red is red shifted gas. And in this plot in particular, we also include the radial contours, which, as I say, includes the jets, the arms, and the bubbles. We have found that for the Virgo cluster, you can see how the gas move around the cluster core in different directions. You can see here the red shifted gas to the right, and then blue shifted gas to the side, to the left side of the core. So, and the gas is following the radial arms. So this is direct evidence of the outflows and the interaction between the IGN and the ICM. And the red side, we can see velocity errors mapped. Of course, as you move away from the central part, where we have a lot of exposure overlap, and the uncertainties in velocity are larger. But for the central part are good. We have found, as I say, depending on the statistics, how strong is the iron K alpha complex, you can find uncertainties down to 100 kilometers per second. But for Virgo, it is clear that no clear spiral pattern can be observed associated to gas sloshing. So that is probably due to the presence of the AGN, because usually this spiral pattern that we observe in gas these correspond to simulations without jets and more basic simulations. So we are interested in study the velocity structure, so we keep doing some different analysis for this cluster. For example, you can see here the radio image. As I say, you have the bubbles, you have the arms, you have the lobes. So what we did here is, okay, we select regions following the radio contour and the radio morphology, and we extract a spectra for these regions and try to measure velocities there. You can see in the left side, for example, the regions in the top, the numbers, and in the bottom, you can see the velocities in kilometers per second obtained for these regions. So, for example, for region 1, you can see the uncertainty is large, but still there is a hint of a change in the velocity here as you move from the left side to the right side. So when you compare the velocities between the radio arms. But if you analyze the velocity map that we obtained before, for example, so you can compare here region 1 and 2, and you can see clearly the change. There is a significant change in the velocity when you move from one direction to the other along the radio arms. So again, this is a very clear evidence of the interaction with the AGN. We also know that for Virgo cluster, there are some cold fronts, which can be observed in the surface brightness, for example, maps of the cluster. And we measure velocities for the cold fronts. There are at least 2 identified here in this cluster. So for the velocities, we found large uncertainties in the velocities. For example, you can compare here the velocity between region 1 and 2, and you can see how large the uncertainties are. This is expected from simulations of gas sloshing, for example. And at the same time, we found that the metallicity changed significantly when you move from one region to other. The change in metallicity is also due to gas sloshing. So in one hand, we have seen hints and characteristics of AGN interaction with the ICM. And on the other hand, when you analyze the cold fronts, you can see also characteristics of the gas sloshing just by the analysis of the velocities. So for the Centaurus cluster, we did so the methodology is very similar. We have new observations. This is a large program. We are talking about 700 kiloseconds. We have multiple observations in offset to cover the central part of the cluster. And you can see in the bottom right, this shows the distribution of the statistics for the Aron K alpha complex. So in this case, for the central part of the Centaurus, we have very good statistics to measure velocities. So this top left panel shows the velocity map obtained for Centaurus. Again, the blue means blue shifted gas and red means red shifted gas. There is no clear spiral pattern. It could be also that the line of sight is perpendicular to the sloshing plane. That also could be a reason for that. This can be seen in simulations when you change the line of sight, depending on the sloshing plane, you will lose also this spiral pattern. And then you can see also a blue structure here with large velocities, blue shifted gas. And this could be associated to the system NGC 4969, which contains powerful AGNs. So this could be also a hint of the impact of AGNs. Before going forward to talk more about the velocities, I also want to mention that we also create maps for temperatures and metallicities. You can see here the temperature distribution and metallicities for the central part of the cluster. But these metallicities and temperatures should be taken carefully, at least in these first papers, because we were only interested in the velocity, so we exclude the soft band in the analysis because we were looking just for the velocity of the Aron K alpha complex. But we are working now in the soft band. I will show some results later. But I just want to mention that, yes, we have these really large exposure observations with really large exposure times, and we create also 2D maps in future for analysis of other parameters like individual elements, for example, the abundance of individual elements. So for Centaurus, we also have cold fronts. We can identify 3 cold fronts near the cluster center. And we measure the velocities, so you can see the regions when you move from one region to the other in the cold front. We measure the velocities. You can see, similar to the Virgo cluster, that the uncertainties are large. The velocities tend to be close to the system velocity. And this is expected from simulation of gas sloshing. But when you measure the metallicities, in this case, we are talking basically about the iron metallicity. You can see how the metallicity change between the core fronts. But interesting, so the regions 3 and 4, this core front is closer to the cluster core. And you can see how the metallicity, the change in the metallicity is not as evident, for example, when compared with regions 1 and 2. So then this could be also a hint of the interaction with the AGN, because you are moving closer to the cluster core. So again, there are hints of both effects, gas sloshing and AGN interaction. And then we have Ophiuchus. Ophiuchus is another gain, I will say, because this is a hot cluster. We are talking about 10 kilo electron volts of temperature, usually peak temperature. There is also another challenge, is that Ophiuchus is close to the galactic plane. So you have really large column density there. But still, the Aron K alpha is is really strong, and we have measured velocities also in this system. So you can see here, this is the X-ray image of the Ophiuchus cluster. And the exposure maps, again, as I say many times now, offset observations in order to cover the central part of the cluster, because you have the Cooper hole in the middle of the detector. And here you can see the statistics of the Aaron complex for this system. So the velocity map of Ophiuchus is the most intriguing one, I would say. We have found regions with really large velocities. We have found, in particular, this interface here. And you can see the gas moving from red shifted to blue shifted gas dramatically. The Chandra observations, for example, do not cover this region. So this is the only X-ray observation that we have for this region. Is intriguing, of course, this interface here. And you can see if you for the central part of the cluster, change in the velocities, and we are talking about 1,000 kilometers per second. Okay, so what is going on? That's the question. Because as I say, in many clusters, not Ophiuchus in particular, but in many clusters, low velocities have been found. But also, as I mentioned before, for the Coma cluster and from simulations, depending on the line of sight, depending on the system, there are regions where you can find high velocities of 1,000 kilometers per second. In particular, for simulation that includes mergings. And there are hints for mergings for Ophiuchus cluster in the past. So it could be that we are identifying signatures from these merging events in the past. Also, there are some velocities, high velocities, that follows the high velocities of the galaxies for those regions, because in general, the velocities obtained for the galaxies from optical observation for Ophiuchus cluster tend to be also really high. But more intriguing, I would say, is that when we look this interface and the change in the velocity, it lies in discontinuity of the surface brightness. So you can see in the top, bottom left panel, the surface brightness of the cluster is kind of symmetric, but in the right side, regions 6 and 7, you don't see such interface. But in the left side, you see the change in the velocity. So this velocity, this interface is located between this discontinuity. So this could be, as I said before, because of the extension, because of the velocities, a signature of a gas, of the merging of the system in the past, instead of AGN, of course, because this is really large, the extension of these regions, and the velocities are really large. And then we measure velocities for different regions following the surface brightness. You can see the change here in the velocity as well. So in general, when you measure different regions for a Ophiuchus cluster, you can find velocities, large velocities, but this interface is one of the most intriguing signatures, and deserve more analysis, of course. For example, Chandra observations. Let's see. Another interesting thing about Ophiuchus is that there is a claim for a radio fossil located south west of the cluster core. So we analyzed regions following this radio fossil that was claimed before, and we measure velocities, temperature, and metallicities there. In the case of Ophiuchus, because the large absorption due to galactic age, the metallicities here are more or less the metallicities that you can obtain, even when including the softband. But for the velocities, there are hints of change in the velocities when you move from one region to another, when you follow regions within the radio fossil, but temperatures and metallicity do not change so much. The uncertainties are large also. So even when we have hints of changing velocities, we cannot make a strong claim about the presence of not of a radial fossil from the X-ray observation. So that was like the first stage of this war, I would say. Now we are in the second stage of the analysis, because we have large exposure time for these observations. We have beautiful spectra. We have very good statistics, especially near the cluster core. So we are now analyzing the metallicities of individual elements, using including also the soft band for the analysis. Because as you can see here in this plot, we are able to measure abundances for oxygen, neon, magnesium, silicon, argon, calcium. So this is the analysis of the chemical enrichment between the cluster, basically. So for Virgo cluster, we create these radial profiles by extracting spectra following these circular regions, these rings of which follow the radial profile of the cluster from the central part more or less to the outskirts. For this analysis, we now include also the astrophysical background, not only the instrumental background, and the astrophysical background is obtained from the observation. Like you can see, the white regions were selected to obtain the astrophysical background, which is still include the contribution, we will say, of the cluster itself. So when modeling the background, we also include the contribution of the cluster, because although we are far from the cluster center, we are still more or less in the region of the contribution of the ICM there. But then we can measure radial profiles for temperatures or metallicities of individual elements. To account for the presence of the multi-temperature component of the ICM, we model the gas with a model called log norm, which follows a log distribution of temperature. So this is not single temperature, not double temperature, but a distribution of temperatures. And we can see, you can see here without uncertainties in this plot, just for clarity, the distribution of the elements. And then we also compute abundance ratios, and we try to model the metal distribution with different supernova models, trying to recover the metallicity distribution of the ICM. But all of this is in the context of the velocities that we are measuring, right? So we did this similar analysis for the other sources as well. For the Centaurus cluster, for example, you can see here, again, the X-ray image, the rings for which we obtain the radial profiles, the regions for where we obtain the background, astrophysical background. And you can see the distribution of temperature, the distribution of the sigma value, which corresponds to the width of the distribution of temperatures. And you can see also the distribution of abundance. Now, with CCD, and especially with EPIC, there are many limitations already. I think we all know that, for the abundance measurements in particular. Why? Well, for example, for the neon line, you have a blend of lines there. You have in the same region nickel, iron, and neon emission lines, and they are blended together. So it's really hard to identify individual element abundance here. For example, for magnesium, you also have the presence of aluminum, which is an instrumental, a really strong one, emission line. So we are definitely in the limits of what we can do. And then when you try to model this with supernova models, we end adding more, I would say, uncertainties in the analysis. But still, I think that there is a lot of information that we can get from this. And for the Ophiuchus cluster, we did a similar analysis. In the case of Ophiuchus, we are more careful, I would say, about hydrogen column density, because as I say, it's located close to the galactic plane. You have to take into account the presence of dust, for example, and not only the atomic hydrogen. But for Ophiuchus, we have, and also you can see in the spectra how weak are the lines for the soft band, oxygen, magnesium, because it's really heavily absorbed, this system. But still, we have, by first time in this case for Ophiuchus, radial profiles for elements like calcium, argon, which have not been done before. So that's the second stage. The third stage will be to do the spectral maps of individual elements and the distribution of them, and particularly try to see correlation, if any, with the velocity maps. So that will be the third stage of this project. But there is also one kind of analysis that we already did for these systems, and I'm referring to the velocity structure functions. So the velocity structure functions allow us to measure the driving scales of different interaction, for example, the AGNs, etc. This VCF, the analysis of the VCF is commonly done with H-alpha measurements. But here we have, I would say, by first time direct observation of velocities in the line of sight. You can do the VCF analysis here too. So the first thing that we did in this particular work is to study the probability distribution function of the velocities, which are assumed to be Gaussian. So what we did is a series of tests of normality tests to be sure that they follow Gaussian distribution, and they do. And for Ophiuchus, there are hints of a multimodal distribution of the velocities, which is also observed in merging systems from simulation. So there are hints of what is going on for Ophiuchus from this kind of analysis. But then you have the velocity structure functions themselves here, and you can see the Virgo is the blue points, the Centaurus, the red, the green ones, and Ophiuchus, the yellow. The uncertainties are large, of course. You can see, for example, in the right, the red points correspond to the H-alpha, but well, we cannot beat H-alpha with XMM for sure. But still, you have a lot of information here, because for Virgo and Centaurus, you can see how the VCF changed and became flattened, and the scale, the separation scale when this happened is around 10 to 20 kiloparsecs, which is also the scale of the radio bubble. So this is giving you a direct indication of the driving scale of the AGN interaction with the ICM. But then for Ophiuchus, you see that the curve do not flatten in that way. It could be that for large separation scale, Ophiuchus flatten a little bit, and that could be the presence of the radio fossil, because the separation scale is more or less 150 kiloparsecs. But again, the uncertainties are large. But for sure, you can see the difference between a system with a powerful AGN in the center part and without it. Yes, and we also did calculation of dissipation time from these curves. We know that it's larger than the jet activity cycle, so we already know that, but we need more heating processes, such as mixing with hot bubbles to reach equilibrium. Again, for the right panel, you can see the comparison with the H-alpha measurements, and the flattening of the curve is we see the flattening of the curve in different scales. So it could be that we are measuring effectively different scale of this the impact of the AGN, but we need, of course, better measurements, which will be obtained later on, not with XMM, to do proper comparison. So let me check the time. Good. Yes, we are reaching the end of our presentation, and of course, the reason why we are talking about this today is because of Athena. So we have here a plot of a beautiful illustration of Athena. I took this plot from the latest white paper that was sent in November, I would say so. So this should consider the new requirements. As I mentioned before, and in this table, you can see a comparison between LEM, Crescent, and Athena. As I say before, all these observatories, especially when you have high resolution spectra, all of them include the velocity of the ICM as an important science case. Because as I say, or I hope to have convinced you about that, there is a lot of information that we can get just by measuring velocities. You will see signatures of gas sloshing, of the AEN, of outflows, driving scales. There is a lot of what we can do, and we are definitely pushing the limits of the current instruments to do that. But with Athena, which is definitely by far way better than other observatories proposed in the sense of effective area, resolution, etc., we will measure in detail the velocities. So a lot of work has been done, by the way, about the results that we will obtain with Athena. A lot of simulations using the instruments have been done. And here I show you just some plots of the, you can have an idea of the resolution, of the spectral resolution. We are talking about uncertainties down to 20 kilometers per second, which is fantastic. And also Athena had has a large field of view compared, for example, with Crescent. So with Athena, we were able to measure not only the central part of the galaxy cluster, but also up to the outskirts, which is also important. Here you can see a comparison of the Athena Hitomi for the Arion K alpha line of a Perseus-like cluster. You can see it's fantastic. With Athena, we also measure viscosity, because you can, with very good detail, measure the dissipation of scale of turbulence. Also, you can do much better than current observations. Analysis of the velocities when you move within the cold front, and then you can study in more detail the gas sloshing structure there. And also, when you have the presence of pore AEN with Athena, you will measure velocities in detail, and you can analyze the outflows, for example. This will be, I would say, groundbreaking for our knowledge of the galaxy cluster, for sure. So in conclusion, the velocity structure in galaxy cluster is important, but it is really hard to do it. So we want to do it. And now using XMM-Newton, we have found a way to do this with uncertainties down to 100 kilometers per second, which again is, I would say, remarkable when we are talking about CTD resolution. Our analysis of Virgo and Centaurus shows hints of both gas sloshing, but also AGN outflows and the interaction between the AGNs and the ICM. And for Ophiuchus, we have found a very intriguing interface with changing the velocities, regions with large velocities, and these points are to maybe the merging in the past for this system. We are doing spectral math for also individual elements, temperature in detail. That will be done this year, I hope. And also last year, another program was approved, and we will observe the system A3266. This is a merging system, so it will be a nice addition to our sample. And I just received an email just now that the first observation will be done, hopefully June 13. So it's on the way. Great. And of course, we are in the limit of what we can do. Athena observations are crucial. The resolution, the field of view, the spatial resolution, spectral resolution, everything. That will be a game changer in this case. Finally, but not less important, there's the synergy between numerical simulations, MOX observations, and real data is necessary to interpret these measurements correctly, because many of these results are intriguing, and they only can be understood understood in the context of simulations, what we can obtain from simulations, etc. And that's it.
Great. Thank you very much, Efrain. That was really fascinating, beautiful results. And I'm excited to see really clear observational evidence that the velocity structure in the intracluster medium has a very interesting spatial distribution. I think your results show this more clearly than what we've seen before. And it highlights the fact that we don't just want to measure these velocities somewhere, we really want to map them. And that is what the Athena XIFU is designed to do. And you clearly show that it's necessary and it's going to be interesting. It's not just, we're going to measure the same velocities everywhere. We're going to find some interesting and puzzling things. Great. Well, let me open the floor for discussion and for questions. If anybody has a question, please raise your hand, or you can type the question into the chat, whichever one works for you. I see a question from Megan. Can we promote Megan so she can speak?
Hello.
Hi.
Hi, Megan.
Hi. I guess I don't have a camera, but yeah, no, very, very interesting talk. And I think also, you know, you not only showed the importance of spatially measuring the velocities, but also measuring these velocities in different systems with, you know, different histories and physical situations. And I wanted to add one additional science case for measuring the velocities in clusters, and that is that, you know, simulations tell us that the turbulence in the hot medium is important for stimulating thermal instabilities, right? So in the cores of clusters, it'd be very interesting to get measurements of the turbulence compared to the velocities you'd expect from just motions due to the gravitational potential. So there's some distinct predictions out there from simulations, and they're testable, and that's the kind of thing I think the people who evaluate the science cases of these missions like to see. So I would add that bullet point because I think it's going to be interesting for these future missions. I wanted to ask a technical question, I guess a technical policy question for XMM. So there's this, you know, new way of improving the energy scales for the EPIC cameras. And we heard a little bit last month at the users group meeting about the possibility of incorporating some of those improvements in the calibration to the pipeline or to the tools that are available to the community. Do you know anything about that, or do you have any comments about that? Is this ready for broader distribution or use, or is it better kept in the hands of experts for now? Because there's you understand that you can get slightly different solutions depending on exactly which instrumental lines you use as your primary calibrators.
Yes, well, I want to mention that in all the calibration process, we have been in contact, of course, with the people from XMM. And in fact, we provide them the calibrations files that we get at the end, just because, yes, they show interest on, okay, let's check this and try to incorporate them in the SAS software. I don't know about specific date for that, but I know that they want to include that. Yes, and in the calibration, for example, this was done in Sanders 2020, but in my first work with the Virgo cluster, we include more observations. We redid the calibration, I would say, which the results were the same, basically. And the calibration also includes or considers the variations in time for these emission lines, as well as the spatial variation. So in that sense, I think that we are in good communication with the SAS people, and I know that they want to include this, but I don't know when. Yeah.
Can I ask a follow-up question?
Sure, sure.
How much time variation do you see? I mean, is it possible that you could do pretty well with one calibration, or is it inevitably going to be something that you're going to have to do a custom calibration for each observation?
So for the calibration, what we did first, there is variation a lot. We are talking about the 20 years of XMM.
I know,
so right. So for the calibration, what we use all the data in the archive for galaxy cluster. We have some constraints on statistics, etc. But we use not only the calibration observations, but also all the observations in the archive. And so these calibrations files that we produce are based on all the observations, not only one source. And then for the observations that you want to analyze, you can use these calibration files, which already consider variations in time, variations in the spatial distribution of the emission lines. So that's it. So we have this calibration files that you can use for all the observations, basically. Yes.
So I think Megan sort of scooped the question in the Q&A that was asked similarly by Daniel Wang. It was also about the stability of the PN gain. But Daniel, you should be allowed to talk. Is there something you want to add or ask in addition?
Can you hear me?
Yes.
Oh, yeah, thanks. So my comments are very similar to Megan's, but also I was thinking about the relative gain. I mean, use the instrument line to calibrate the gain, but also at different energies, also relative, say, at different energies, how the gain based on your calibration. I just want to get some sense how the relative gain changes with time, because many years ago I worked on with the Suzaku data a little bit. I know quite a bit of change, even relatively, between the different energies. And also another question is whether you think the same technique can be applied to the Chandra ACIS data.
Okay, so as I say, we first, there is one reason why we don't include in the first stage the soft band, and it's because, yes, the calibration, the improvement in the calibration is close to the K alpha line. Because you move to lower energies, you have to extrapolate that, and it will not be good. So we are talking about energies about 4 kV to apply this energy correction. That's one thing about the energy, the limitations in the energy scale. Lower than that, we are not applying the calibration. We are using the standard one. Also, as I said, we use all the archive data. So we have analysis of the correction factor for each CCD, for each a function of time, I would say. So all this analysis was done in 2020 and also in 2022. And regarding Chandra, well, I am not an expert on the instrumental side of Chandra, but a college of mine here at MPE start to look for it. So I don't know if it can be applied and how, but I know that some people are, of course, started to think about it. Yeah.
Yeah, can I ask a follow-up question?
Sure.
I understand you did a lot of calibrations. So I just want to get some sense, say, whether the gain change, for example, is monotonic or kind of random. Can you kind of predict reasonably well, how the gain changes, especially relatively speaking? I mean, even say, I understand that you use the lines which are close to the, say, iron line. That's certainly a good strategy. But there's a different instrument lines, for example, whether the relative gains changes between different instrument lines.
Right. So I will share, if I can, here I hope I'm sharing the paper. Maybe it's a paper in the screen. Yeah.
Mm.
Okay, so this is Sanders 2020. So this is where you find all the details on the calibration, right? So we have, as I say, you can see here for example, the fitting, the Cooper K alpha redshift. You can see the variation with the revolutions, and you have two sets of data here: full frame, extended full frame. So we have kind of a difference in the data to analyze, but you can see the change in the Cooper K alpha redshift. And then you can see also the variations, the spatial variation of the redshift. A function also on time, you have the revolutions indicate in these plots as well. And we have done, so we feed this variation basically to know the relation. And here, this is the energy scale correction for the CCDs as function as time. So you can see the correction that we have applied. It's not, I would say, not random, but yeah, we have fit these variations. Yes, I mean, I can point out this paper in more details about the.
Okay, thank you.
Yeah, you're welcome.
Okay, and then we have a very nice announcement, I think, from Norbert Schartel on the chat. Norbert, do you want to tell us yourself?
I know.
Yeah, I simply want to comment that this calibration was made available for the general public with the last release of the SAS, and this is about a month ago. It is not exactly the same because the calibration was different now compared when this was originally done. But this is now generally available. Please read the documentation.
Perfect. That's good. Good to know.
On that note, I don't see any other hands raised. I think this is a great announcement to end with. So please, everybody's welcome to try it on their own analysis and see what they get. And it is 4 on the clock. So I want to thank everybody for attending. Again, especially given Pentecost today. And thank you very much, Efrain, for a great talk. It led to a lot of discussion. Clearly, people are interested in these results. So congratulations on this wonderful talk. And
thanks.
With that, I think we don't have a scheduled next installment for the next series, the next part of this webinar series. But as you well expect, the Athena Community Office will be in touch about the schedule. So please check the announcements, and we would love to see you at the next edition of these seminars. So thank you very much, everyone.
Thank you.